We've spent a long time talking about functions. We've seen that we can define functions, we can call functions, we can declare functions. We've also seen that function calls can be placed inside of any expression. And so we know that since main is a regular function and it's common to call functions inside of main, that it's completely logical to call a function from inside of another function. And we've also done a lot of torturous function tracing exercises that show us that it's an everyday occurrence for a function to call another function. But here's a question. Can a function call itself? And the answer is yes. So let's do this exercise. I want to talk about a numerical quantity called factorial. And so to compute factorials, you multiply together 1 times 2 times 3 times 4 up to a number. So for example, 3 factorial, we use an exclamation point for that, equals 1 times 2 times 3. And so that would be 6. 4 factorial would be 1 times 2 times 3 times 4, which equals 24. And then 5 factorial would be 1 times 2 times 3 times 4 times 5, which happens to equal 120. And so we can see if you want to compute factorials, what you do is you multiply together every integer from 1 up to the number that you're computing the factorial of. Okay, that's one thing. The next thing is, maybe you'll notice there's a pattern forming here. 4 factorial, buried inside of it, I've got 3 factorial. And 5 factorial, buried inside of that, I have 4 factorial. In fact, maybe I could even write it like this. 4 factorial equals 4 times 3 factorial. Got to work on my 3's. And 5 factorial equals 5 times 4 factorial. That's interesting. Maybe that'll make it easier to compute. And so for this exercise, you should try writing a loop to do this. You can do this with a loop. But I want to talk about something else. I want to talk about a design technique called recursion, which is immensely powerful. It is in fact more powerful than loops. And it turns out that we could actually do everything with recursion if we wanted to. It would never be necessary to write any loops if we did everything with recursion. But there are lots of reasons why loops can be convenient. So, what does it mean to compute factorial? Well, the first thing is, what do we do about strange cases like 0 factorial? Okay, well, the function specification actually gives us a way out there. So it says, if I ever ask you for the factorial of 0 or a negative number, we'll just call that 1. Now, the next one is, what about 1 factorial? Okay, so 1 factorial is just equal to 1. So it's the product of all of the integers from 1 up to and including the thing I'm taking factorial of, so 1 factorial is equal to 1. Here's how I'll write that. Okay, so if n is 0 or negative, so if it's less than or equal to 0, then I return 1. If n is less than or equal to 0, then I return 1. And I guess I'll put this in curly brackets. We already know that we don't have to use curly brackets on one-line if statements, but it can be a comforting thing to do. Okay, if n is less than or equal to 0, return 1. Okay, next question. Do I know how to compute 1 factorial? Because maybe I'm fed up with using loops. Maybe I don't want to think about how to design a loop after all this time. I just can't stand it anymore. Can I make any progress on this problem? Well, yeah, I guess I know what 1 factorial is. If n is equal to 1, then it's 1. And you know, I could say, hey, if n is equal to 2, then I return 2. And if n is equal to 3, well, I've already worked out 3 factorial, return 6. But of course, I can't keep doing this all day. I can't make an if statement for every single value of n. Okay, that's not going to work. But I do have n equals 1. That's fair enough. I could use an if statement for that. And then I ask you, okay, you get a value that's at least 2. Because we know that with these 2 if statements, that covers the case where n is 0 or negative and the case where n is 1. Which means if I get down to line 25, I haven't already returned from the function, and that means that n is at least equal to 2. So what's 2 factorial? Okay, so 2 factorial equals 1 times 2. But 2 factorial also equals 2 times 1 factorial. And 3 factorial is also equal to 3 times 2 factorial. Well, that's interesting. So if you give me a value of n that's at least 2, it looks like there's a pattern forming. So n times n minus 1 factorial. So in fact, I could write that out. I'm running out of space. I could write that out. N factorial equals n times n minus 1 factorial. So maybe that's how I could compute my factorial in the function. I could say, well, when I have a value greater than or equal to 2, the value of the factorial is n times the factorial of n minus 1. Damn it. If only I had a function in my program that could compute oh wait, yeah, I do. It's this one. Here's a function to compute factorials. That's what it says it does. Who's to say I'm not allowed to use that function? That's a bit of a provocative thing to try. So I'm going to clear out my drawing here. So what I've taken advantage of is the fact that I have observed that n factorial equals n times n minus 1 factorial. And I think, well, if that's good enough for the mathematicians, that's good enough for me. If I can compute n factorial by multiplying n minus 1 factorial by something, why can't I do it in code? Can't I just call my factorial function for it? And it turns out that the answer is yes. And take a moment to appreciate this, because your brain might want to twist itself in a knot with a function calling itself. So the key thing to do here is believe. If you've written your function correctly, isn't it reasonable that it will tell you n minus 1 factorial if you ask? Well, yeah, that's its job. And so if we believe that the function works, we could use the function to help write itself. So we'll try that out. 5 factorial is 120. Let's try 6 factorial. 6 factorial is 720. And you can go verify that's correct. That is, in fact, equal to 120 times 6. And so what I did was I wrote a repetitive process, 1 times 2 times 3 times 4 times 5, without using a loop. Instead, I used a function that called itself. And it almost seems like cheating. There's so little work being done here. And it's because I've been able to break my problem down. I've taken a pretty complicated problem of how to compute a factorial, and I've broken it down into simple steps. Hey, you want to compute a factorial? Take the number you currently have and multiply it by a slightly smaller factorial. I found a way of taking a problem, peeling away a little bit, and then I end up with a smaller instance of the same problem. So what I've actually found, this observation over here, is a recursive decomposition of the problem, a way of turning the problem into a smaller version of itself. And if we think about it, that means that 5 factorial equals 5 times 4 factorial, which equals 5 times, okay, we got to draw this out, 4 times 3 factorial, okay, which equals 5 times 4 times 3, wish I could draw 3s, times 2 factorial. And you might notice it keeps expanding further and further down, breaking it down into smaller and smaller versions of the factorial problem until eventually we're talking about 1 factorial. That's the next step. 5 times 4 times 3 times 2 times 1 factorial. And you might notice that my function doesn't need any help to compute 1 factorial. If it keeps calling itself and chipping away at the problem, eventually it'll prune the problem all the way down to the case where we're computing 1 factorial. And then it just returns 1, and then it's done. And so what we have here, these two if statements, are what we would call the base case of a recursive decomposition, where the problem is so simple, for example, when n equals 1, that you don't need any help to solve it. And if you can turn more complicated versions of the problem, like n equals 2, n equals 3, n equals 4, if you can find one of these recursive decompositions, a way of chipping away and turning the problem into a smaller version of itself, then over time, the problem will sort of unravel until you get all the way back down to the base case. And so here I've used recursion to compute factorial, and it's completely valid to have a function that calls itself.